We are talking about atomic structure today, and it's a really exciting topic. I love it, really. It's a good mix of storytelling and really important scientific discoveries, and we kind of see how we ended up where we are today in terms of our understanding of the building blocks of the universe. So, the first time we hear of the word atom is actually quite a long time ago. It's around 450 BC, and this guy here, an ancient Greek scientist and philosopher Democritus, was the first one to suggest that maybe all matter in the universe is composed of these tiny little particles that we cannot divide any further. And atomos in Greek stands for indivisible, so he gave them that name, atomos. Of course, that's where atom comes from. And we completely forgot about this and let go of this information and focused on other things for a very, very long time until John Dalton comes around, and this is second half of the 18th century, early 19th century. So almost 2,000 years go by, a little bit more, and we return to our notion of atoms. John Dalton was an English scientist and a school teacher, and is known today as the father of modern atomic theory. So he kind of brings the idea of atoms back. He suggests that all elements are indeed made of atoms, that atoms of the same element are alike in mass and size, and we're going to see that this is almost true. It's not 100% true. Atoms of different elements differ in mass and size. And yes, that is true. If we look on the periodic table, and we're just only now beginning to do so, if we look at the very top, we have hydrogen as the first element, and it's a tiny, tiny little element. And if we look on the bottom of the periodic table, and we have things like lead or uranium or mercury, those are really big, heavy elements, and their size is big, and there's a lot more mass in that. He also suggests that atoms combine in simple numerical ratios, and that's when we form compounds. So he leaves us with two big ideas. The first one is called the law of definite proportions, and it states that chemical compounds are formed by a union of two or more atoms of different elements. So we need at least two different elements combining in order to form a compound. If it's only one type of element, then we just keep the name element and that's it, right? There's no change. One atom, one element, several types of different atoms, it's a compound. And if you're brand new to chemistry, which probably many of you are, the way we can tell it in writing is if we have two symbols beginning, each starts with a capital letter, and they're written right next to one another without any space in between. The second is the law of multiple proportions, and it states that different ratios lead to different compounds. And there's some examples, and I think examples are easier than the words in this case. We have a compound, H2O. You've probably heard of it. It's water. We have hydrogen and oxygen, capital H, capital O, no spaces in between. Numbers, sure, but no spaces. So two hydrogens, and this means one oxygen. If there is no number, it means one. On the other hand, we have another type of compound, H2O2. It's the same elements, hydrogen and oxygen, but in different ratio, two H's and two O's. This is hydrogen peroxide, so maybe it's something you have in your medicine cabinet at home. So in both cases, same element, but different ratios, and that means they're different compounds. Another example, we have NO and 2O5, and really there are many of these. And then our atomic discoveries start to pick up a little bit. So now we are in the second half of the 19th century. Now it's only about 50 to 100 years gap. And a British scientist, J.J. Thomson, discovers an electron. And electrons carry a negative charge. Letter Q stands for charge. So this is charge is smaller than 0, right? So negative. And we discover later on that mass of the electron is tiny, 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 9.1 times 10 to the negative 28th of a gram. And you're now familiar with scientific notation, so that means that we have 0.27 zeros 91. So you can imagine just how minute it is. And onwards we go. So now we are mostly in the 20th century, early 20th century, the first maybe 10, 15 years of it. And we encounter Ernest Rutherford. He is from New Zealand originally, grew up on a farm, and really enjoyed physics toys, all kinds of magnets and pulleys and that kind of stuff. And so he attended university in Canada and then found a job in a lab in England. And he is known for the discovery of nucleus and of protons in 1911. And he's a really, really cool guy. So a little bit about his discovery. Protons are positively charged. So here's that same letter Q for charged, but now it's greater than 0. And their mass is 1.67 times 10 to the minus 27th of a kilogram. So you could see still obviously tiny, but a little bit less so than the electron. And in fact, each proton is about 2,000 times heavier than an electron. So really, relatively speaking, a big difference. So a little bit about the way all of this got discovered. It's a really cool experiment. Over here, we have a box with a source of radiation. So there's a little bit of radium sitting inside the box. And radiation, X-rays had just been discovered. People weren't quite sure how they work and what they do and what they can be used for or anything. So everyone wanted to play with them. So Ernest Rutherford did too. So he has a source of radiation. The type of radiation is alpha particles. And I make a note here. Alpha particles are actually helium ions, so that might also not be very informative, but they are relatively heavy, relatively large particles, and they carry a positive charge. So we have this beam of heavy positive particles that just emanates from this box. It's very regular. There's no interruption. So on the count 1, 2, 3, 4, all the time consistently, we're going to get these alpha particles coming out. This yellow square here is a gold foil, and it's a very, very thinly hammered out gold foil, only a couple of atoms thick. And all around is this green fluorescent screen. And it's useful because whenever an alpha particle hits the screen, you can see a little flash. And so if we're sitting in a dark room, which is the way the experiment was conducted, Hans Geiger, the same guy who created Geiger counter, actually conducted this experiment. He was a student in the lab, or a lab technician. So he sat in a really dark room for a long, long time and counted tiny little flashes and noted their location. So let's move on and see the observations that we make and then the conclusions we can make from their observations. So here's that same setup again, just so it's kind of fresh in our mind. So once again, a recap of the experiment. We have a beam of alpha particles that's aimed at a thin piece of gold. So heavy positive particles are aimed at gold. What do we actually observe? Most alpha particles go straight through. And you can see on this cartoon, most of them hit the screen right there. Yeah, there's a piece of gold foil, and these are pretty big particles, alpha particles, but they go right through gold as if it's just completely empty space. We also notice that a couple of alpha particles get deflected, so we see maybe one here, not often, but once in a while. And we see very rarely in this cartoon just once that maybe it got deflected, meaning it bounced all the way back. What do we conclude based on this? Based on our first observation, we conclude that atoms are mostly empty space because we have a big particle that goes through gold as if it's not even there. So cannot be anything there, mostly empty. Inside an atom is a very small, very dense nucleus. We get this conclusion from really the second observation mostly, right? Because our alpha particles go through the atom very easily, and we say atoms are mostly empty space. And of the flip side of that is that nucleus must be tiny, right? If we have an atom this size and it's mostly empty, then the nucleus is just tiny little dots sitting in the center. And it must be very, very dense because our big alpha particles are able to bounce off of it. Even though nucleus is just a tiny dot, this big thing going at it still can bounce back. So counterintuitive a little bit in terms of size, perhaps, which is suggesting to us that maybe whatever it is that the alpha particle hits must be really, really heavy. And our last conclusion is that nucleus is positively charged because our alpha particles bounce back or they deflect, right? We know alpha particles are positively charged themselves, and because they bounce, it probably means that whatever it is they hit has the same charge as they do. Because at this point, we already know that same charges will repel. If they were of opposite charges, they would attract, right? So a positive alpha particle would just get stuck to the nucleus if the nucleus were negative. It does not do that. It bounces, probably not negative. So we conclude based on this, these three really important observations, that atoms are mostly empty space, nucleus is tiny and very heavy, and also positively charged. Even more time goes by, and in 1932, yet another British scientist, James Chadwick, discovers a neutron. And neutron has a zero charge. It's neutral in charge and has the same mass as a proton. If you're wondering why neutron was so long to discover, it's because it is neutral and it's much harder to detect if it has no charge. So now we need to put it all together. And there are several ideas and theories about what, atoms might look like. But Niels Bohr comes around, and this is still first, 20 years of the 20th century. And he creates a model of a hydrogen atom. And based on that, all of our further understanding is developed. So we know protons are positively charged, so we say a charge of +1. Neutrons are neutral in charge, or have a charge 0. Electrons are negatively charged, or -1. Protons and neutrons live inside the nucleus. Both of those, so the second and the first item here, this is our nucleus. Electrons go all the way around, and sometimes we say electrons orbit the nucleus. And they're very, very light and small. Electrons are 2,000 times smaller than protons, so most of the mass of our atom is concentrated inside the nucleus. And we end up with something that looks like this. So we've got a nucleus in the center. Overall, it's a plus charge because neutrons, even though they're there, they do not contribute a charge. And electrons go all the way around.